joining us today, we have Bryony Horgan. Bryony is a professor of planetary science at Purdue University. So thanks for joining us, Bryony.
Yeah, glad to be here.
We appreciate you taking time, especially with a young new one here. It's hard to get away sometimes, literally hard to get away. We understand that, but you're balancing a lot on your plate right now with everything that you're doing. With are you doing any summer classes or anything?
No, just a lot of research and missions and baby, which is a lot of fun altogether.
Well, really, any one of those would be a full-time thing. So, but yeah, I know you're getting ready to take some time off from the from campus for the mission, right? That's coming up.
Yeah, so Mars 2020, the next NASA rover, the Perseverance rover, will be landing in Jezero Crater in February 2021. So we're really excited about it.
It's going to be landing where?
In Jezero Crater on Mars.
It's all right. So you were on. You had something to do with this, from what I understand. The landing site. Before I say something totally wrong, explain this to us.
Yeah, so you might wonder, okay, how does NASA decide where to send a rover, right? How do you decide where to send this, $2 billion rover you're building, your one chance to look for signs of ancient life on Mars? And the way NASA does it is we hold this, it's a long process. It takes a couple of years. We have these big community meetings where all the scientists from, all over the world get together and talk about where they want to send this rover. And then eventually, you vote and you have discussions, and NASA has some internal decisions, and you eventually, whittle it down to a couple of sites. And so I was really fortunate to help on the Mars 2020 team with studying and sort of evaluating Jezero Crater as one of the candidate landing sites. And so I actually got to go in and look at the satellite data and actually think about, what the rover would do and, what kind of science we could do there, and then help present that to the community. And out of that process, NASA ended up selecting Jezero as a landing site. So it's been really cool to actually think about going to the place that we've been staring at in satellite data all this time.
So, how many different places were proposed?
Oh, so the first meeting was 2015, I think, and there were, I think it was 50 or 60 different landing sites kind of thrown out there, and got it down to, something like 20, and then something like, I forget if it was 12, and then 7, and then 3, and kind of this, many meetings. It's a lot of fun though, right? It's actually, I tell my students, it's some of the best, sort of most entertaining science you'll see, and some of the best science, because people really have strong opinions, and they'll really try hard to defend them. And so it's one of the few times you really get to see science happening in front of you.
Oh, wow. How many people would be on a team deciding something like this?
So the actual decisions are made, at NASA headquarters, or ultimately made by the NASA administrator. So really, it's sort of all this input comes from the community, from the science team on the mission, also from their sort of a select back room of folks who help kind of make a more informed recommendation that also goes to the administrator. But ultimately, it's the guy in charge who decides where to go. But they chose a great site, so I think it worked out well.
Well, and this was the site that your team was proposing, right, originally?
Right. So actually, I started out proposing a totally different site, and it's one that another rover is going to go to, the ExoMars European rover, which is supposed to launch next year. It's been delayed, so hopefully in 2 years. That's actually going to a site called Mars Vallis, and it's totally different kind of place on Mars. We think it's this really ancient surface environment with wetlands and all this stuff that used to be there. But so Mars 2020 isn't going there, but we hope ExoMars will get there eventually.
So this what was it? Jezero,
yeah, Jezero.
Jezero Crater. What? Tell me, geology. Why? What's interesting about this thing?
Well, so you have to go back to what is the mission going to do, right? So what is this specific rover trying to do? And so our previous rovers we've sent to Mars have, we started out with Spirit and Opportunity going to Mars to look for signs of water, to try to, show that, yes, there was, in fact, water on ancient Mars. And they showed that in buckets and buckets, right? They found tons of ancient watery environments, all different kinds, hydrothermal systems, lakes, playas where water's evaporating, all kinds of things. And then Mars Science Laboratory, the Curiosity rover, followed up on that by saying, okay, now that we know there was water, Now we can try to go figure out whether or not that water was actually a place where life could live, if it was habitable or not. So to do that, we had to send this big complicated rover that could look at the chemistry of the rocks and try to understand the chemistry of those ancient watery environments. Could they have supported life? And so that's what Curiosity's been doing, and it found evidence for this long-lived habitable lake environment in Gale Crater. Probably was there for maybe even millions of years or more. And now that we know, this is kind of gradual stepping up process, right? Now that we know there was water, we know that that water was habitable. Now we can finally send the rover we've been wanting to send for decades that's actually going to look in the ancient rocks on Mars for signs of ancient microbial life. Now that we know, that it was habitable, now that we think we kind of know where we can go looking for it, where it might be preserved, we can actually do that. So that brings you to Jezero, right? So why do we think Jezero is a good place to go look for those signs of ancient life? Well, one thing, it's probably the best example we have on Mars for evidence of an ancient crater lake. Because in Jezero, there's this big lake delta. So a delta is what happens when a river flows into a body of water, either an ocean or a lake. It leaves this big kind of wedge of sediments behind. And so we see that in Jezero. We see this ancient dried up delta. And so that tells us there used to be a lake in this crater. We also see all kinds of cool minerals that might have precipitated out of the lake. So things like carbonates, which form when you have dissolved carbon dioxide and other stuff in the lake, and then precipitates out to make, beautiful white beaches and things along the margins. And what's great about all those things, these kind of minerals that precipitate, the delta depositing these sediments, both of those places are places where you might expect to preserve signs of ancient microbes. In the delta, you have these muds that are forming at the far end of the delta, kind of out in the lake. You can trap lots of organic molecules and bits of microbes and things there. On the beaches and places where minerals are precipitating out, that's a really great way to trap organics and stuff too. And so between all those different kind of mechanisms for preserving signs of life, that's the reason we chose Jezero, because it has lots of different ways we might expect to find signs of ancient life from billions of years ago on Mars.
Wow. All right, so I want to ask about the life in a second, but before, and Sarah, you can interrupt me or wave if I'm being too, I'm just so excited. If I'm being too greedy at the questions at her time. All right, so a planetary geologist, when we talk about, because you're like, oh yeah, we know there was a lake there. And people oftentimes come to me and they're like, but how would we know that? And so explain how a planetary geologist figures out things about a planet based on well, I'll let you me answering the question that I do.
Yeah, so when I'm not working on rover data, I work with data from NASA satellites around Mars, both from NASA and other space agencies around the world. And so we use satellite data to look at the planet and try to understand, what is the geology of the surface telling us. So for example, if you want to understand the history of water, we look for things like ancient river valleys that are dried up now, which we see crisscrossing the most ancient parts of Mars. This delta is a great example. We can see it in the orbital imagery as this kind of beautiful sort of preserved big triangular wedge of sediments with rivers carved into it and all of that. The other thing we do to try to understand water in particular is to look for minerals. So from orbit, we can actually identify minerals on the surface using a technique called spectroscopy, where we look at sunlight reflected from the surface. Different minerals will absorb different wavelengths of that light. And by looking at those fingerprints of those minerals reflected back from the surface, we can tell which minerals are there. So we can look for things like salts on the surface, right? And salt is a good example because it forms usually in water, it precipitates out of water, and it's left behind when water evaporates, right? And so we look for things like that. And on Mars, we've seen so many examples of all different kinds of minerals that tell us about all kinds of ancient watery environments, hydrothermal springs like you might find at Yellowstone. We see evidence for lakes. We see evidence for, ancient soils forming from rain falling on them, kind of all sorts of different things. So we try to put that all together to get an idea of what, this planet might have looked like billions of years ago based on what's left in the rock record.
But there's no, currently evidence of water anywhere on the planet, is there?
Well, so there's lots of water frozen up in ice, right? So there's enough water frozen in ice on Mars. There's a little bit in the polar caps, but actually most of it's frozen just underground. There's tons of ice frozen underground on Mars. If you melted it, you could easily make an ocean, right? So there's actually a lot of water. There's just not much. There's just not a lot there that's liquid. We're still not totally sure if there's much liquid water on Mars today. If there is any, it's very little and it's very, very salty because that's the only way You can keep water liquid at cold temperatures just to make it really salty. And we've seen a little bit of evidence for that, but it's really controversial. So if there's any, so there's a lot of ice, and if there's any liquid water, it's probably pretty deep underground. There are some ideas about maybe there are these deep biospheres on Mars where, we have microbes living today, but in liquid water environments, but they're deep underground where it's still warm.
Oh wow. Uh, oh wow. So when we, sorry, uh, with the, what rover is it called?
Perseverance?
Yeah. Perseverance. Is it, will it end up bringing samples back, or is it just analyzing there only? How's that going to work?
So the rover itself, what we're going to try to do is look for signs of ancient life and then also collect little drill samples of rocks that we think might contain those signs of ancient life. We're going to do the best job we can looking for what we call biosignatures with the rover. But, especially since we're talking about ancient Mars, we're talking about microbial life, it's really hard to find clear evidence for ancient microbial life in rocks, right? That's a problem we have on Earth. We don't know a lot about the origin of life on Earth because it's really hard to track microbes through the geologic record. So to do that well, we really have to bring those rocks back to Earth. So this rover is going to collect those samples, and they're all going to be these kind of pencil-sized, sort of thin little drill cores that we're going to encase in these little tubes. And what we're going to do is actually send another mission to go grab those drill cores and bring them back to Earth. And we're calling that Mars Sample Return. And it's this huge effort. It's really something we've been wanting to do at Mars, not just NASA, but, all planetary scientists all over the world for decades now, because it's really we think one of our best chances for finding signs of life outside of the Earth is to get these rocks back from Mars into our labs, look at them with our amazing microscopes and other techniques we have back here on Earth. So it's a really exciting set of missions. It's actually really complicated because you have to think about it, right? So you have this rover, so we have these samples, they'll be ready to go, well characterized, all of that. But then you have to land on the surface, which is hard because landing on Mars is really tough already. Then you have to rove over to either the Perseverance rover or whatever depot we leave our samples at to get the samples, bring them back to a launching platform, launch them from the surface of Mars into orbit, and then you have to capture that sample package in orbit with another spacecraft, bring it back to Earth, and land on Earth. It's super complicated, and that's the reason we haven't done it yet, because we're kind of just getting to the point where we have the technology to do it. So it's also expensive. That's another reason it hasn't happened yet. And so the way NASA is getting around that now is they just signed a big agreement with the European Space Agency. Both agencies are going to work on it together, and Europeans and NASA are going to sort of split it up and do different parts. NASA is going to build some of the hard things, like the spacecraft that lands on the surface, and the Europeans are going to build the rover. But together we can kind of share the cost and hopefully do the science together when we get back to. So it should be really exciting.
Now, will there be? Okay. Last question, then Sarah, take over. This is what I'm dying to ask. Now, is there any chance, and what kind of chance would there be that any of this life is not fossilized, but possibly like living microbes?
That's a great question. This is actually something NASA worries about a lot because there's a whole idea in NASA called planetary protection. So planetary protection is the idea that one, you don't want to bring back anything to Earth that's potentially harmful. And so that's why, when you bring things back from other planets, they have to be sort of either sterilized or really carefully controlled. But you also don't want to necessarily contaminate other planets with Earth life, right? Just from kind of a preservation point of view, you don't want to, contaminate other planets and mess them up, but also because that makes it a lot harder for us to understand what's going on with extraterrestrial life. There's a bunch of Earth life bumming around. So one of the consequences of that is that NASA doesn't let us send missions to places where they think there's even a tiny chance that life might be living today on Mars. So that's places like where we think there might be some sign of liquid water near the surface. There's also they also don't like us sending anything nuclear powered to where there is subsurface ice, because if you crashed that spacecraft and you had this nuclear powered thing that was warm and it melted the ice, that would create this little refuge for Earth life that could then grow. So they're really, really careful about where we can send missions. So for this mission, we're not allowed to send it anywhere where they think there's a good chance there might be living life today. But there are other, let's cut out for a second. There might be other places where we can do that. So there are other mission ideas that are being really carefully thought of going to some of these icy places and looking for modern life, or drilling deep into the subsurface to look for life. But this rover we're sending now isn't going to do that, just because we don't think we'll find it there, but also the rover isn't really set up to look for living things. It's set up to look at the rocks.
Okay. All right, Sarah, I promised I'd let you. I'm sorry.
Yeah, no, that's fine. That was a great question. Well, I'm listening to all this. I had no idea. I didn't even think about like planning out where you would send a mission or where it would land. So that's just fascinating to me, first of all, there. But then you've mentioned that a lot of this, it takes decades. You can't be many decades old, like you're young. And so how does all this planning, like if it extends decades and decades, and this is something we've been wanting to do, how do you, because humans like have to, we're not that old once we get into it, how does that happen? Like how do you continue the growth of this? Because I'm thinking like people that maybe even like that are just being born today someday are going to like step in and continue with this plan. So can you speak a little bit about how this plan continues, because it happens over such a long period of time?
Yeah, I mean, so there definitely are some folks still around that worked on the earliest rover missions. So like the Pathfinder lander and the Sojourner rover back in the 90s. There are still folks around that, that were grad students back in the days and they were working on that. And they're the ones that are leading some of these missions today. But definitely it's, getting students involved. So like a lot of my work, I have, a big group of grad students and a bunch of them are working on these rover missions. So they're learning, how to work on a rover, how to interpret the data, how to interpret satellite data, making sure that they get out and do geology back here on Earth too, so they have that kind of reference point. But they're being trained to kind of take over eventually, right? And it's a really great point. Planetary science is kind of weird in that way. It does take decades. Right now, we're talking about, there's ideas about maybe sending a mission to Uranus or Neptune, but it takes in some cases more than 10 years to get there. It might take you another 10 years to plan. So you're talking about missions that are doing things in like the 2040s. So that's, hopefully I'll still be around at that point, but it's more likely that it's, my students and postdocs right now, they're going to be doing a lot of that science, which is really exciting. So it's planetary science is a weird thing. It has this really long time scale. And that's one of the things that makes it really fun, but also kind of stressful because you have to worry about, oh, do I know what I'm going to be doing in 10 years? So yeah. So I mean, NASA facilitates this because we have the Mars Exploration Program, and that's really the goal of the whole Mars Exploration Program has been, Mars 2020, looking for signs of life in Mars sample return. So we've been building up to this rover for, ever since Pathfinder landed in the 90s, and you could argue even going back to the Viking landers in the 70s, which were our first landers on Mars that, first tried to look for signs of life. We've been really building up to this for a long time, and so we're really excited. It's also a lot of pressure, but we have a great team and a great rover. So
Well, thank you. That's awesome.
So, do we know why the surface has changed and why there's not lakes, or what could have? Do we have ideas? I know we don't know, no, but do we have ideas on what might have changed at Mars?
that's a great question. Yeah, because what we're talking about is, all this water I've been talking about, mostly this is like 3 or 4 billion years ago that we think there's evidence for liquid water, lots of it on the surface of Mars. And today it's all frozen, it's very, very dry, and the surface is really cold. The reason that water isn't stable today on the surface is because the atmosphere is too thin. To have liquid water be stable, you have to have a thick enough atmosphere to keep it there. Now the atmosphere is so thin that water can only be stable either as a gas or as a solid as ice. In between, it just the water will just boil away. So we think what must have been different in the past is that Mars must have had a much thicker atmosphere, probably closer to what Earth has. Right now the atmosphere at Mars is something like 1/1000th or 1/100th of the thickness that we have here on Earth. So it's really thin, right? You can't breathe it. But 3 or 4 billion years ago, it must have been a lot thicker. So you have to say, okay, where did it go, right? What happened to it? So we think there's a couple of things. One, some of it probably got blown off the planet, by early solar wind can strip atmospheres from planets. Also, big impacts from big asteroids and things hitting can also strip off some of the atmosphere. And also just Mars, it's a much smaller planet than the Earth. It only has about, it's about half the size of the Earth. And so because of that, the gravity is a lot lower. And so over time, really light gases can actually just escape and they can just, literally be stripped away, kind of puff out and escape the planet. And so all those things together, we think, have led to loss of the atmosphere. What we don't know is how much there was to start. And that's one of the big questions that NASA is trying to answer is how much atmosphere has Mars lost? That's how you figure out, how warm, how wet, what kind of environments really were there. And so, we're hoping that some of the samples we're bringing back with Mars sample return will tell us that because we can look at things like the specific minerals that form from the atmosphere, like carbonates that come from carbon dioxide in the atmosphere. Have isotopes and things that tell us about how much atmosphere was there when they formed, and so that's one of the reasons we really want to do Mars sample return too, is to figure some of this stuff out.
I know a lot of the climate change scientists here on Earth talking about how climate change, they look at like the ice core records and stuff like that. Do you expect that we'll learn more about the climate that was on Mars when we look at if we get ice cores in their so many words? Is ice actually in those cores that we get?
Yeah, that's a great question. That's actually one of the mission ideas that's floating around right now. It's kind of one of the next, what's the next big thing we're going to do on Mars, after sample return or while we're working on sample return. And one of the ideas is going to the polar caps and either, drilling or having a rover that can kind of rove up the side of the caps to basically do that, to basically get an ice core and see how the climate has changed recently. The ice caps are a lot younger than the kind of rocks we're going to see in Jezero. They're probably, millions of years, tens of millions of years, maybe at the most hundreds of millions of years. But they can tell us about how the climate has changed on Mars recently. And we know it has. We see evidence that, there used to be glaciers in this part of the planet and now they're gone, just like here on Earth. We see evidence that, ice has moved around, all of that. And so if we can figure out more about how the climate on Mars works, that'll also help us understand how the climate on Earth works too and how it changes over time. It helps us refine our climate models and atmospheric models and all of that too.
Well, and do we expect that eventually the data that we get from Mars, will that then be to give us insight to what we need to either do, stop doing, or not do here on Earth to prevent something like us being on Mars in a few more billion years?
I mean, the good news is we'll never turn into a Mars because the Earth's so big it's going to hold on to its atmosphere. And so the problem is that means you're going to keep in the atmosphere whatever you put into it, though, right? And that's probably the problem we have here on Earth is you have to worry about all that stuff we're putting into the atmosphere right now sticking around for a long time. So there are some things we'll learn. Like on Mars, one of the big mysteries right now is methane. So methane, it's a greenhouse gas back here on Earth, and it might be important for keeping Mars warm in the past, but it's weird because we see it on Mars today. There's been observations showing it in the atmosphere. But methane isn't stable. It should be broken down by sunlight and the atmosphere and all of that. So where is it coming from on Mars? One possibility is that it's coming from life that's living in the subsurface today, that it's actually a biosignature in the atmosphere. We're not sure, and that's one of the ideas. It could be coming from, or it could be coming from water interacting with rocks deep underground too. We're not really sure, but that's definitely, learning more about methane and why it's there, why it's stable, why it's hanging around is something that might help us again kind of understand our atmosphere back here on Earth a little better too.
Oh, that is so cool. So, in another, I mean, what Sarah say? You're several decades old. Is that what she said?
Sure.
Hundreds of decades or something like that. So,
No, you can't be.
In another
You can't
dozen
be that many.
decades, in another
Yeah.
dozen decades, when you look back and you're like, all right, I was a planetary scientist. You're more geology than anything else, right? Planetary geologist.
Right.
And so, wait, what are you going to say? Okay, I was successful because, or beyond successful because we learned what?
That's a great
It's a weird question, but I'm weird.
I think it's going to be about how to look for life because I think that's what NASA has been learning over the past couple of decades is how do you do it? Because if you go back, so I mentioned Viking earlier. So Viking were these two huge spacecraft, the first two really successful missions that landed on Mars. And their goal was they said, okay, we're going to land on Mars. It's been this place that we've thought might support life for hundreds of years based on looking through it at telescopes and things. We're going to look for, microbes living in the soil on Mars. So the Viking landers landed and they tried to, take some of the soil and grow it, try to grow the microbes in there. They tried to look for organic molecules in the soil and just basically more or less totally failed. It turns out we just didn't know enough. For example, they were looking for organic molecules in the soil and they didn't see them. It turns out they're actually probably there. We just didn't know what to look for. When we do the same kind of experiments today, we see byproducts that tell us that, yeah, there are organic molecules in the soil on Mars today. Probably not from life, probably from meteorites and things raining down, but they're there. And the life experiments too, they're really ambiguous. They basically tried to mix some growth media in with the soil and see if anything came out. And they saw all these weird gases come out. And so now we know, okay, that at the time it was really controversial, is that sign of life or not? But now we know what's in the soil on Mars. We can say, no, that's probably just a reaction with some minerals that were in the soil. So we know a lot more now about that. But from those missions, NASA, it took another 20 years before NASA figured this out. But they said, okay, we need to actually think about how to look for life. It's a really hard question, especially when it's microbes you're talking about. And that's where the Mars exploration program came out of, is saying, okay, we first need to know whether or not there was water. Then we need to look for a habitable environment. And then we can go look for a place where that life might be preserved. So now that we know all these things, we've actually taken a lot of those lessons learned and we're applying them to other places like Europa. It's one of the icy moons in the outer solar system of Jupiter. We're talking about just building these new missions to go to Europa to look for signs of life. And we're following that same kind of progression now at Europa that's worked so well at Mars, even exoplanets, right? So outside of our solar system, now we kind of know, okay, what do we know about habitability versus looking for actual biosignatures? How do you do that? And we've learned a lot from that process. So I'm really hopeful that the cool thing, I really hope we'll find some signs of extraterrestrial life in, a couple decades. That would be awesome. But even if we don't, I think we'll know so much more about how to do it that we'll be on the right path to doing it pretty soon.
Oh, that's cool. I like that answer. That's a good answer. It was a weird question. You answered it well too. All right, so a high school student. If a high school student is listening to this right now and they're like, "Whoa, this is so cool," which it is, they'd be right. Now, what do we tell them? I just had a high school student give me a look. She can only hear half the conversation, the things I say, and she looks back in like, "What?" But what do we tell them that they would want to study or to focus on in high school so that they could be successful and possibly one day being on a team looking for life somewhere?
Yeah, well, the one thing you really need to be a planetary scientist is you need a college degree in some kind of hard science. It doesn't have to be planetary science. It can be, it could be geology, chemistry, physics, even math, biology. All those things will work. You have to get that. And to get that, you need to take, as much math as you can in high school. It's really important. If you can get an opportunity to learn how to program, that's also really great. It's better. It's like learning a language. The earlier you do it, the easier it is. So that's really awesome. And also look for opportunities to get involved. I mean, NASA has internships for high schoolers. There are all kinds of cool opportunities to do, outreach with NASA. And just keep up with what's going on. And eventually you can actually get involved. It's really cool. I have undergrads here at Purdue that help analyze rover data with me and have been on papers with me talking about science, a Gale crater with Curiosity. So there are ways to get involved early on, but for sure, taking a lot of math, if you can, it helps a lot.
And I just wanted to point out too, you had said hard science, and I think just for every student listening, that doesn't mean necessarily that it's that you can't do it. It's not that it's difficult, but it's the difference between what they call a hard science and a soft science. And so the sciences that you're speaking of, like mathematics, chemistry, physics, biology, like those things, they're referred to as hard science classes, but it doesn't mean that not doable. So,
exactly. Yeah, no, it's totally true. You also don't have to do, if you're worried about not being good at math and doing science, you don't necessarily have to be, right? Math is something you learn how to do and you do it. It's a tool. I actually don't do that much math day to day in my job, but doing math, doing physics, and learning how to do it is so important for learning how to think through science problems, right? That's really what you're learning when you learn how to do those things, is how to think critically, how to do science. And so even though I don't do a lot of math, having all that background has been really, really helpful for me.
Awesome. Oh, we so appreciate this. We appreciate your time. This was really awesome.
Yeah, thank you so much.
It's always fun to talk about Mars. So,
yeah.
Hey, I'll be honest. Full disclosure. I mean, I knew that there was ideas that there was probably water on Mars before, but I didn't realize there's that much evidence.
I didn't either.
Yeah.
I mean, like, wow, I kind of feel like, ooh, I missed the ball because, I mean, your office is, not far from mine. And, and I didn't realize that. I'm like, oh, this is embarrassing.
Hopefully soon I'll have an actual rock that was made in a lake on ancient Mars that I can show you. It'd be great.
That'll be so
Wow.
cool.
Oh my gosh. How
I just
cool.
want to know what they find. I want to know what they find.
Yeah.
Oh, the question I forgot to ask. Cheryl will be so disappointed in me. Let me ask you one more question. Yeah, even though I thought we were done, I was just rambling at that point. Because Cheryl asked me to ask, how can we have it? When this is going to land,
Right.
but you have this big window of when it's going to take off.
Right, yeah. So there's a big 2 week window when the rover can launch from Florida, from Cape Canaveral, and we have a window because storms or all this stuff might make it so you can't launch the first opportunity you can. And there's only a specific time we can launch because you need to have Earth and Mars lined up in the right way. Because the way it actually happens is we launch the rocket from Earth, and Mars it catches up to Mars and then lands on Mars. So they have to be in the right kind of orbital configuration. But what's really cool is even though we're launching in this big 2 week window, we know what day and time it's going to land at because we know exactly where it's going to land on Mars. And so Mars has to be pointed toward us the exact right way so that we can hit that landing site coming in from Earth. So to do that, once we launch, the engineers will actually, use rockets on the spacecraft to either slow down or speed it up so that we can make sure to hit the bullseye when we get to Mars. And the bullseye is tiny. The bullseye is our landing ellipse place we expect to land is something like 8 kilometers across. I mean, the equivalent is insane. It's like a sniper shooting someone the other side of the planet it's insane how accurate it is. And the engineers are doing an amazing job getting us to Mars and getting us there.
Wow.
That is just mind blowing. I mean, the fact that you could within a 2 week window, sometime you're gonna toss something off the Earth and you're gonna have it land at a particular day and time at an exact location that's just crazy. That's awesome.
Yeah, it's great.
That is so cool. Wow.
All
Okay,
right.
thank you. This is just awesome.
Yeah, happy to help.
Thank you for listening to our podcast. Please hit the subscribe button so you'll continue to hear about new and exciting STEM-related work being done.
Tweet us questions, suggestions, and requests at Purdue SOS, or email us at k12science@purdue.edu.
Until next time, be super, and remember, you are someone's hero. Boiler up.
Hammer down.